one more lecture related to fluid mechanics and hydraulic machines, and myself, Dr. Padala Rajshekhar, Assistant Professor, Department of Civil Engineering, School of Engineering, SR University, Warangal, India. And before going to the lecture, we will see the recap of previous unit, whatever we have discussed till now. The first unit, fluid statics, focuses on understanding how pressure varies in fluids and at rest and how it will be measured. That is what, and it begins with the definition of a fluid and concept of continuous and basic fluid properties like density, specific weight, specific volume, and vacuum pressure and compressibility and elasticity, as well as some kind of things, viscosity, surface tension. These all basic things we have seen in fluid properties, and then fluids are then classified into different types based on their behavior under force. Pascal's law and hydrostatic law explains how pressure acts in all directions and increases with depth. And moreover, pressure measurement using manometer and mechanical gauges helps us observe and calculate fluid pressure practically. And this knowledge sets the foundation for the next unit 2, where we study how fluids exert force on surfaces and affect floating and submerged bodies. That is what our next unit agenda. So now coming to the point, hydrostatics. See, when we are storing on water, here we have stored a water and we have to release the water. So how much pressure is having at this point and what is the force required and with respect to the height. That means hydrostatics is a branch of fluid mechanics that deals with fluids at rest. It focuses on analyzing the forces exerted by or on fluids that are not in motion, particularly due to pressure. That means fluid mechanics that we know, but it is specially dealing with at rest. So we are storing some kind of water. It focuses on analyzing the forces exerted by or on fluids that are not in motion. That's what we are telling, which are in stored place. So we have to use it for some others also. We have to open the gates, particularly due to the pressure. Applications: design of dams and retaining walls, as well as hydraulic lift and presses and water storage tanks and pressure calculations. So it's all things comes under hydrostats. Okay. So water storage tanks and pressure calculations. Now we will see some kind of problems related to the height, related to the force, and related to the pressure and everything with respect to the gate. So these are the practical examples. Hydrostats, as we discussed in previous lecture also, if you are taking depth, this is the depth. So if you are having outlet point is here, it is high pressure, and here low pressure, and here medium pressure. So here we are storing the water. If at all maximum water floods occurs, then we are lifting this gates. And this is the one thing where the pressure, like previous one, you see this is the water and this is the gate. In the similar way, this is the water and this is the gates. And see, when you are releasing the water from dam, hydrostatics example. Now total pressure and center of pressure. When a static fluid comes in contact with surface, that means whenever plane are curved, it exerts a force on that surface. So static fluid comes in contact with a surface, it exerts a force on that surface. This force is called total pressure. Understood? And coming to the another one, since a fluid at rest does not exert any tangential shear force, that is also correct. When it is at rest, it won't show any kind of force. The total pressure always acts normal to the surface. That means total pressure is nothing but perpendicular to the surface. The point at which this total pressure acts is known as center of pressure. So whenever it is in acting position, uh, the point at which this total pressure acts is known as center of pressure. You can see in many hydraulic engineering applications such as design of dams, gates, tanks and retaining walls, engineers must calculate both the magnitude of total pressure and the exact location where it acts on the surface. So they have to go with respect to magnitude of total pressure as well as the exact location where it acts on the surface. That means in a simplified way, you see there are four cases of submerged surfaces on which the total forces and center of pressure can be determined. The submerged surfaces may be horizontal, vertical, inclined and curved. So it is having four types. There are four cases of submerged on which the total pressure forces and the center of pressure is to be determined. That is horizontal, vertical and inclined surfaces. The submerged surfaces may be, you see, it's curved, horizontal, inclined and vertical pressures. Now first one we'll see horizontal plane surface. When a surface is held horizontally and completely submerged, each point on that surface lies at the same depth from the free surface of the liquid. Now you see this is the free surface of the liquid and this is a horizontal plane, and you see this is the pressure and this is the height. So what they are telling, when a surface is held horizontally and completely submerged, each point on that surface lies at the same depth from the free surface of the liquid. Because of this, the pressure intensity remains constant across the entire surface. And this uniform pressure acts perpendicularly, that is normal to the surface, and produces a resultant force known as total pressure. Since the pressure is uniformly distributed, this total force is known as simply P is equal to rho into A, where rho is equal to W into H, WAH. The W is equal to specific weight of the fluid, P is equal to total pressure. Now importantly, this force acts vertically downward in the direction of gravity and passes through the centroid of the horizontal surface. And next one, coming to the vertical plane surface. Considering a plane vertical surface of arbitrary shape immersed in a liquid as shown in figure. That means you see here free surface liquid is there and here some dH is there. So here the first one, this is gravity and this is pressure, center of pressure, and G is center of gravity of the plane surface. Now H bar is nothing distance of the center of gravity of the area to the total surface, and H star is nothing but the free surface liquid to the center of pressure, distance of center of pressure from free surface of liquid, and this is called B width and this is A to B section, and the force is acting this side, and dH is a small thing we have taken. Considering a plane vertical surface of arbitrary shape immersed in a liquid as shown in figure. Let A equal to total area of the surface, H bar equal to distance of CG of the area from free surface of liquid, and G is the center of gravity of plane surface, and P is equal to center of pressure, and H star equal to distance of center of pressure from free surface of the liquid. So now another one, we are going little forward. Total pressure. The total pressure on the surface may be determined by dividing the entire surface into a number of small parallel strips. And the force on the surface is then calculated by integrating the force of small strip. As I mentioned, this one, dH is nothing but a small strip. Considering a strip of thickness dH and width B and depth H, pressure intensity on the strip P is equal to rho GH, area of the strip is equal to dA is equal to B into dH. The total pressure force on strip equal to pressure intensity on the strip into area of the strip. So dF is equal to P into dA, that is equal to rho GH into B into dH. Total pressure force on the whole surface, that is equal to F is equal to, see we know P, that is equal to rho GH, dA we know B into dH. Now integration, just do integration, rho GH into B dH, that is equal to, you take out constants of rho G and H into B into dH. But integration of H into B into dH is also known as integration of H into dA. As we know, dA is also known as B into dH, where integration of H into dA is nothing but movement of surface area about the free surface of liquid dA, that is equal to area of surface into distance of CG from the free surface, that is equal to A is equal to A into H bar, that is equal to force equal to rho G A into H bar. Simple, rho G A into H bar. rho g a into h bar. Now center of pressure is nothing but the center of pressure h bar is nothing but the center of pressure is calculated by using the principle of moments, which states that the moment of resultant force about an axis is equal to the sum of moments of the components about the same axis. See, here we have seen h bar, that is nothing but free surface of the liquid to the center of pressure. So now the simple definition, center of pressure is nothing but is calculated using principle of moments, which states that the moment of resultant force about an axis is equal to the sum of moments of the components about the same axis. The resultant force F is acting at P at a distance h star from the free surface of liquid. Hence, moment of force F about free surface of liquid equal to F into h bar. But moment force dF is acting on a strip about the free surface of liquid. So dF into h, that is equal to rho g h into b into dh into h. So sum of moments of all such forces about free surface of liquid, that is equal to rho g h, as we know, b into dh we know, into h. Rho g is constant, h into b into dh into h, that is equal to rho g b into h into h square into dh. Already we know b into dh is nothing but dA. So integration of h square into dA is equal to moment of inertia of the surface area about the free surface liquid, that is called I naught. Now sum of moments about free surface equal to rho g I naught. F into h bar is equal to rho g I naught. That is equal to F is equal to rho g into A into h bar. And we know that rho g A into h bar into h star is equal to rho g into I naught. Just now we have seen I naught. Then h bar equal to rho g I naught by rho g into A into h bar. So h equal to I naught into A into h bar, that is equal to by the parallel axis theorem. We have I naught equal to Ig plus A into h bar, where Ig equal to moment of inertia of area about an axis passing through CG of the area and parallel to the free surface of liquid. Substituting Ig equal to h bar Ig plus A into h bar by A into h bar. Ig is nothing but moment of inertia. Moment of inertia by A into h bar plus A into A Ig by A into h bar plus h bar. Vertical plane surface are some of the things: plane, surface, area, and moment of inertia, because we are discussing of the moment of inertia. Rectangle, triangle, circle. Rectangle is nothing but b into d, triangle is nothing but b h by 2, and circle is pi d square by 4. Area of rectangle is b into d, whereas moment of inertia b d cube by 12. Triangle is bh by 2, whereas moment of inertia bh cube by 36 into iaa is equal to bh cube by 12. And circle is pi by 4 d square, as we know, and here moment of inertia is pi by 64 into d power 4. So next one problem we will see, we'll try to understand. A rectangular plane surface is 2 meters wide and 3 meters deep. It lies in vertical lane of water in water. Determine the total pressure and position of center of pressure on the plane surface when its upper edge is horizontal, coincides with water A, coincides with water surface B. It is with respect to 2.5 meters below the free surface of water. If it is coincide, that means first we have to determine total pressure and position of center of pressure on the plane surface when its upper edge is horizontal and coincides with the water pressure. Now you see right side the diagram, observe it. Free water surface, it is having a depth of 3 meters and width of 2 meters. And this is gravity, this is pressure. With respect to gravity is h bar, with respect to pressure is h star, as we know from previous diagrams. Here you can see, that's what we have mentioned. Now we will see the solution. Width of the plane surface B equal to 2 meters and the depth of the plane surface D is equal to 3 meters. And case upper edge coincide, first one it should coincide, right? Upper edge coincides with water surface as shown in figure. That is nothing but total pressure is given by the equation F equal to rho G A into rho G A into H bar, where rho G equal to 1000 kgs per meter cube of water. A is nothing but area, that is B into D, that is 3 into 2, that is 6 meters, and H bar is half into depth, half into depth, because it is rectangle, that is 1.5 meters. Therefore, force equal to rho G into A into H bar, that is equal to 1000 into 9.81 into 6 into 1.5. That is equal to depth of center of pressure equal to H bar is equal to, now we have to find two things, H bar and Ig. H bar is equal to Ig into A into H, H star equal to Ig into Ig by A into H bar plus H bar. So H star is equal to, Ig is nothing but, we will calculate with respect to moment of inertia of the area of the surface, BD cube by 12, 2 into 3 cube by 12, that is 4.5 meter per 4.5 meter per 4. Agree? Now substitute Ig. Ig we know, A we know, H bar we know. Just substitute it, you will get So h bar equal to 4.5 by 6 into 1.5, that is equal to plus 1.5, that is equal to 2. Now this is for first thing, upper edge coincides with water surface as shown in the figure. Now we will go with upper edge is 2.5 meters below the free surface. So that is what the difference we can see here. Now just understand what we have to do, then it will be easy aspect. See, total pressure is given by the equation F is equal to rho G into H bar, obviously. Next, rho is equal to 1000 kgs per meter cube, and area is equal to 3 into 2, 6 meters per second meter square, and H bar is equal to 2.5, that is the depth, and 1 by 2 into 3, that is equal to 4 meters. Therefore, force equal to rho G A into H bar. So rho is equal to 1000. So F is equal to 1000 into 9.81 into area is 6. That is equal to 3 into 2, 6. And H bar is 4. So total force is 22,35440 newtons. And next, depth of the center of pressure, H bar equal to H star equal to Ig into A H bar H dash plus H dash. So before that, Ig, moment of inertia of the area of the surface, we have to calculate. That is equal to BD cube by 12. BD cube by 12. B is 2 and D is 3. 2 into 3 cube by 12. That is equal to 4.5 meter per 4. So just substitute H star equal to Ig. So H star equal to Ig by A into H bar plus H bar, such that Ig is 4.5, we know that, and A is 3 into 2, 6, we know that, and H bar already we have calculated, that is 4. So totally we understood 4.1875 meters. So once again we'll see. A rectangular plane surface is 2 meters wide and 3 meters depth. It lies in vertical plane in water, and determine the total pressure and the position of the center of the pressure on the plane surface when its upper edge is horizontal and one is coinciding, another one is 2.5 meters below the free surface. That's what we are seeing here. They given B is equal to 2 meters and D is equal to 3 meters. And first one is coinciding, that force equal to rho G into A into H bar. So rho already we know 1000 kg per meter cube, and A is equal to 3 into 2 meter, that is equal to 6 meters square, and H bar is equal to half into depth, that is 3. So we got 1.5 meters. So force equal to 1000 into 9.81 into 6 into 1.5, that is 88,290 newtons. And depth is H star equal to Ig by A into H bar plus H bar. Already we know Ig is moment of inertia, that is a BdQ by 12. So 2 into 3Q by 12, that is 4.5 meter per 4. That is equal to 4.5 by 6 into 1.5 plus 1.5. That is equal to 2 meters. Next we have gone to some depth 2.5 meters below, that is force is equal to rho g a into h bar, that is equal to rho is equal to 1000 kg per meter cube, a is equal to 3 into 6 and h bar is equal to 2.5 depth plus 1 by 2 into d, that is equal to 3, that is equal to 4 meters. So force is equal to 1000, force is equal to 1000 into 9.81 into 6 into 4, that is equal to 235,440 newtons. So Ig is nothing but moment of inertia of the area of the surface. So b cube by 12 by 12. So 2 into 3 cube by 12, that is 4.5 meter per 4. Therefore h star is equal to 4.5 by 6 into 4 plus 4, that is equal to 4.1875 meters. So we'll see the summary of the lecture. Hydrostatic deals with fluids at rest and the forces they exert on surfaces. Total pressure is a force exerted by a static fluid on a surface due to its weight. Center of pressure, already we have discussed, is a point where the total pressure acts on the surface. And coming to the, for a horizontal surface, pressure is uniform and acts at the center of the area. For a vertical surface, pressure increases with depth and the center of pressure lies below the centroid. That is what we have seen today lecture. So try to understand this concept. It will be very useful. If any questions, please comment.